So even more common in weak acid computations is when you have a known equilibrium constant Ka or pKa, and you are given some initial concentration of a weak acid, and you're asked to determine what are the equilibrium concentrations once that system comes to equilibrium or equilibrium pH. So an example of that would be like this, where you have 0.05 moles per liter of HF, which we know already is a weak acid. You toss that into a beaker of water, we know that some amount of that's going to dissociate based on Ka. Ka is small, so to what extent is it going to break apart and produce these constituent ions? And so can we find out what those concentrations are and the ending pH once the system has relaxed to equilibrium? So it can be helpful to visualize these types of problems, and what they're really asking you is, all right, you've got this vessel of pure water, and you are initially going to add 0.05 moles of HF per liter of that water, but we know it's going to break apart, and HF is going to react with water, and so you'll have HF plus water that proceeds to make H3O plus fluoride ion, but the extent of that is not totally clear. That's what we're being asked to figure out. But we do know what the Ka is because often you can just look up the Kas in tables. So this is a more realistic problem because Kas are tabulated for most weak acids. And so that's an accessible parameter. The other things aren't because they are dependent on this unique situation, which you will have to compute. So let's approach this sort of sequentially or systematically and think through several independent steps that you can apply to any weak acid problem, because they're all going to come out in sort of different ways. So less important is memorizing exactly the steps, and more important is the logic that you use to solve this problem. So a useful tactic anytime you're solving multi-component problems, and this is an example of a multi-component problem, is to write out what you know and what you don't know, what you need to find. And so sometimes the process of doing this is helpful to trigger the logic needed to solve the problem. So what we do know is the Ka. We can look that up in a table. It's 3.5 times 10 to the minus 4. We know the initial HF concentration that we're adding to that beaker. That's 0.025. And we know Kw because it's always true. That's 1.0 times 10 to the minus 14. What we're being asked to compute are all the concentrations of all the relevant species and the pH, which is really just the same as H3O plus, but at equilibrium. So what we have are sort of initial conditions, and what we're being asked to compute is equilibrium conditions. So that should hopefully trigger a little bit of thought in your mind that maybe we need this ice table, because that allows us to think about initial change and then compute what the equilibrium condition is. So the first step in solving this is to figure out or write out all the possible reactions. We also want to include the equilibrium constant associated with that reaction. So I'm starting with the dissociation of our weak acid HF into protons and the fluoride ion, and it has this relevant Ka. But remember, this is in water, and what you always know about water, well, water always obeys the equilibrium between H plus and OH minus, which we know is the autodissociation of water. So we should write that up because it's a known. It's something that we know about this. So that gives us something like this. Just notice as a caveat here, I'm not explicitly including water as a reactant, and so I have protons instead of hydronium ions. Those, as we've talked about at length in these videos, are synonymous with the H3O plus hydronium ion, so they're the same thing. So the second step is to just look at the relative strengths of the reactions that you've written up here, and then look at maybe the strongest one to consider, because it's probably the one that's going to be most dominant in the system. And this is sort of an assumption or an approximation we're making. In more advanced classes, we start to consider everything, but that requires us to have special tools like software and or linear algebra to be able to solve systems of equations. But here we're saying, okay, we've got HF and we've got water. both of which are acting like acids here. Which one is stronger? Well, we have their K's here, and we can compare them. The K for HF is 10 to the minus 4, and the K for water is 10 to the minus 14. That means that HF is 10 orders of magnitude exponentially stronger than pure water, so HF is probably going to be the most dominant thing in the system that's providing hydronium ions. So our next step then, once we've identified likely dominant reaction here, which we've considered as HF, we need to tabulate what are the initial conditions for that reaction, and then what would we expect the change to be, and that will allow us to consider what the equilibrium conditions are, which is what we're trying to compute. So we know that the initial condition is 0.025 molar of HF, but we know some amount of that's going to break up. We're going to say that we don't have any protons in water. That's not true. We mentioned before this asterisk really means that there is protons, but they're around 10 to the minus 7, which turns out to be inconsequential when you add that to something much larger than 10 to the minus 7. So we just sort of approximate that as 0 and 0 fluoride. So the stoichiometry here is nice and clean, so this is just a 1-to-1. So we would expect then that some amount of HFX is going to dissociate, and that same X is going to produce H plus and fluoride in 1-to-1 ratio. So our equilibrium concentration is then going to be our initial minus that change, and then we're going to have X amount of both hydrogen and fluoride ion at equilibrium. So the next step should be logical. It's the same one we used before. So once we have our concentrations in terms of X, we need to plug those X values into an expression. That expression is always going to be the equilibrium expression because that's our known. We know what Ka is. We know how to write up an expression for Ka. That's products over reactants. And so we can substitute X for each one of these concentrations, and we get X squared over 0.025 minus X equal to 3.5 times 10 to the minus 4. So now we need to solve this. So of course, to solve this, we could write this out, simplify this, and solve it using a quadratic equation directly. And that's totally fine, and that is always going to give you the right answer. There's also a shortcut involved, which involves an approximation, but the approximation is only valid under certain circumstances. I'm going to walk you through that approximation because it can be really nice and quick, but just so you know, the quadratic is always correct. So you could just skip the approximation, never worry about it at all, get the right answer every single time. It just might take you longer to get there because the quadratic can be a little unwieldy. So the approximation is based on this premise that if Ka is small for the reaction, then we can assume that the equilibrium lies very far to the left, which means that HF in this case doesn't really dissociate much into H plus and fluoride minus. And why that's relevant here is because of this term here under HF. Because if we're trying to figure out what the equilibrium concentration of HF is, it's going to be whatever its initial concentration is minus that change X. But if K is really tiny, then X is also tiny. And so if you're subtracting a tiny number from a bigger number, it may be inconsequential. And so our first approximation is Ka is tiny, X is tiny, and it's inconsequential in this equation down here. We can't get rid of the X up here because when you take a small number and square it, that's consequential. But when you take a small number and subtract it from a bigger one, then that could be approximated as 0. So that's our approximation. So I just rewrote the same equilibrium expression that we have down here, but I said, well, that's so small relative to this number that we're going to call that 0. That, if we then multiply this out, will negate the use of the quadratic equation, as we'll see in a second. So that gives us an equation of this form, which then if I multiply that by the Ka, which we know, we get something that's equal to X squared. So now we can just take the root of this value to get X. That gives us a value of 0.00296. This is X. So, and I notice I put this as an approximate, not equal, and that's because we're basing it on an approximation. We said this X is inconsequential, which allowed us to not use the quadratic equation. So now we need to test this approximation. We need to evaluate, is this reasonable? And the way to check if this is reasonable is to evaluate is X actually big enough to make a difference when we subtract it from the initial concentration 0.025? So let's check that. Simplest way to do that is to just take the actual size of X and compare it directly through a ratio to that number, 0.025. That's the initial concentration, remember. And just see what percentage of the initial concentration, what percentage of 0.025 is X. And if it's a significant percentage, usually we say anything more than 5%, then that's an intolerable amount of error. We don't want more than 5% error in our calculations. If it's less than 5%, maybe we can handle that. So I just wrote this up as our X over the initial concentration times 100%. That gives us almost 12%. That's a huge amount of error in our computations simply by making this approximation. And since this is considerably bigger than 5%, and in some cases 5% is intolerable as well, in some classes and in some circumstances 1% or 0.1% is the only tolerable error. But in this class, 5% is going to be our approximation standard. This is too big, which means that this whole process could have been a nice shortcut, but it wasn't in this case, which means we need to go back to the quadratic equation. Okay, so I'm just replacing that approximation language that I had here with the direct solution via the quadratic. So I'm just rewriting the same expression that we already produced in number 4. Now this X is large enough that we have to include it in this expression. So let's go ahead and write this out in a form that can be solved quadratically. That should look something like this. So here's our A, B, and C. So you can go ahead and plug this into the quadratic in any way that you prefer to solve that. Apologies, I had an incorrect number here. I mistyped that in my calculator, so it should be 8.75 times 10 to the minus 6 as the C term here, so plug that. So the quadratic equation will give you two values, one of which will be negative, so that's clear that that's not an appropriate value. So here's the only one worth saving. I have not conserved the same number of sig figs, so we would clean this up and conserve only 3 digits in this case because that's what we're constrained by, I think. No, 2 digits here, so this will be 0.0028. And since we're not totally done using X yet, we still need to compute another value using X. I am going to use a notation that you haven't seen me use, but it's really common. You don't want to round your sig figs before you're done using this value, and so I am going to write up my value with the 2 and 7 as significant, and then I'm going to have a third digit which is not a significant digit, and I'm going to subscript it here, and that tells me that I'm going to include this in my computations because that'll minimize my error, my rounding error, but I will know I'll be able to carry my sig figs through the next computation, so I don't have to try to remember how many I had. And so remember, the thing that we're trying to compute here are the equilibrium concentrations of everything and the pH. So we need to take X and plug it back into our equilibrium term at the ice table to finalize or figure out everything else. So the easy ones to compute are just HF, H plus, and F. So the fluoride and hydrogen ion concentration are the same because they're both X. So they're here. I've conserved 2 digits here now because these are the final answers. And HF is just 0.025 minus X. So I've conserved those 2 digits as well. But remember, we're also being asked to compute hydroxide ion concentration and pH. Remember, if we know H plus, then we know Kw is always true, then we can figure out OH using the Kw equilibrium expression. That gives us something like this, 3.6 times 10 to the minus 12. Because remember, hydroxide concentration times hydrogen ion concentration will always add up to 1 times 10 to the minus 14. The products will. The last thing is then pH, and we know pH just to be the negative log of the proton concentration, which gives us a value of 2.55. Remember, in terms of sig figs, we had 2 sig figs in our hydrogen ion concentration, and so we conserve 2 past the decimal in the logged version of pH here. So that's everything. We've computed everything that we were targeting. This process will work every single time as long as you break the question up into its constituent parts. So it's important to write out what you know, what you need to find, and then work through the sequence to solve for the values that you need to solve. And as long as you're logical about each of those steps and you're careful about conserving your sig figs along the way, you'll get the right answer every time.